Hi everyone, welcome to another lecture of the MATLAB Crash Course series. My name is Stephen Yagmore. Today we are going to be discussing a few things. We're going to be discussing mathematics, logicals, and other functions with matrices and vectors. So we have quite a few topics that we're going to cover today. So first we're going to look at mathematical scalar operations to perform on matrices and vectors, then mathematical array operations, then we're going to look at matrix multiplication. Then we're going to take a look into the logical aspect with logical vectors and matrices. We're going to look at logical operators with vectors, and then we're going to look at logical functions for vectors, as well as other functions for vectors and matrices. So first we're going to start out by looking at mathematical scalar operations. So a scalar, unlike a vector or a matrix, is a single numerical value. So a scalar is like just a single number, 2, 3, 5.7. All those are scalars. The key, though, is a scalar is a single number. It's not like a vector where you can have multiple numbers, it's just a single number. So a scalar, just any single number, can be used to perform basic mathematical operations on vectors or matrices. So essentially, we can take a vector or a matrix, and we can use a scalar to perform some mathematical operations. So let's take a simple example. So let's say we have this matrix over here to the right. Let's assign it as mat. And let's let k just be some scalar. So mat plus k adds k, that number, to each element of mat, the matrix. So if we added some scalar k, the new matrix we would get would be 7 plus k here, 5 plus k here, 3 plus k, 2 plus k, 3 plus k, 4 plus k. It adds k to every single element. Mat minus k, likewise, will subtract k from each element. Mat times k multiplies k to each element. Mat divided by k divides each element of mat by k. So the best way to look at this is by looking at an example. So I have mat saved right now on MATLAB. I'm going to choose k to be 2. So I'm going to make 2 my scalar. I can perform mat plus 2 right here. Doing that will multiply each element, not multiply, add each element by 2. So 7 plus 2 is 9, 5 plus 2 is 7, 3 plus 2 is 5, etc., etc. We add 2 to each of the elements. Likewise, if we have mat, I can do mat minus 2. It'll do the same thing except we're subtracting. 7 minus 2 is 5, 5 minus 2 is 3. It subtracts each element by 2. Let's clear that. Mat times 2, for example. Let's show what mat is. Mat times 2, just the same, multiplies each element by 2. I could do mat divided by 2. It divides each element by 2. We get more digits here because we're starting to get decimals because some of them are odd numbers. But so essentially whatever operation you want, using the with a scalar, it's going to perform it, except for using exponents. You can't just do this with exponents, and I'll show what I'm talking about in a later slide. But so just know if you want to add, subtract, multiply, divide by any scalar to a matrix or vector, simply just use the operator and it will work as you'd expect. Now we're going to look at mathematical array operations. So let's consider 2 matrices A and B. So A is right here and B is right here. Notice that A and B are matrices of the same dimensions. They're both 3 by 2 matrices. They have 3 rows and 2 columns. The corresponding elements of the 2 matrices with the same dimensions, as we discussed, can perform mathematical operations as follows. Essentially what we can do is we can add and subtract, multiply and divide. We can perform all those operations on corresponding elements of 2 matrices of the same size. And I'll show you what I mean here. So A plus B adds corresponding elements of the 2 matrices. So what would happen if I did A plus B, I would get 1 plus 7, 4 plus 4, 6 plus 12. Each corresponding element would be added to each other. So let's actually do that. So I have A and B already saved in MATLAB. If I perform A plus B, I'm going to get what results if you add the corresponding elements. 1 plus 7 is 8, 4 plus 4 is 8, 6 plus 12 is 18, 3 plus 6 is 9, etc. Simply, the only condition you need is that these matrices must have the same dimensions. If they don't have the same dimensions, MATLAB doesn't know what the corresponding elements are, so it can't perform any operations. Likewise, A minus B will subtract the corresponding elements, so let me show that. So if I do A minus B, we get what happens when you subtract each element of B from each element of A. It's very straightforward. Now we're going to discuss multiplication and division, but this is a little bit different. So if I want to multiply each corresponding element to each other, I have to use the notation A period asterisk B. I can't just use an asterisk here, I have to use the period. Let me show you this. So if I have A and I have B as follows, I can perform A dot asterisk B, and it'll multiply the corresponding elements. 1 times 7 is 7, 4 times 4 is 16, 6 times 12 is 72. All the corresponding elements are multiplied together. But what's important here is that I used a period in front of the asterisk. I'll discuss exactly why I did that in the next slide, but here I can do the same thing with division, but I need to use the period again. B dot slash A will divide the corresponding elements. So let's clear this. So I have B and I have A. If I do B dot slash A, so you can see here it is going to give me exactly what I need. So dividing the elements works the same. 7 divided by 1 is 7, 4 divided by 4 is 1. It works exactly how you'd expect, except you have to use the period in front of that slash again, or else it won't work. Likewise, let's say I want to raise A, just the matrix A, to some scalar power. Let's say 2, for example. If I want to raise each element of A to the second power, I can use the caret, but once again I have to use a period in front of it, or else it won't work. So let's see what A is. If I do A dot caret 2, it will raise each element to the second power. 1 squared is 1, 4 squared is 16, 6 squared is 36. It does exactly what we want. But let's say I didn't use that period, for example, and this goes for the other operations. If I just did A to the second power, it gives me an error and says incorrect dimensions for raising a matrix to a power. To perform element-wise matrix powers, use the period and the caret like we were doing. So why doesn't this work? So the reason why this actually will not work is because the other operators, so just using a single caret or using just the asterisk without the period, that goes into matrix multiplication. So matrix multiplication is a core concept discussed in mathematics courses such as linear algebra. For those who have taken linear algebra, you'll know that matrix multiplication is fundamental for this course. Maybe in Algebra 2 or Algebra you discussed matrix multiplication, but I'm going to give a recap on what it is. This type of multiplication is not the same as the multiplication we discussed on the previous slide. You do not just multiply the corresponding elements to each other. For two matrices to be multiplied using matrix multiplication, the number of columns on the first matrix must equal the number of rows on the second matrix. This is crucial here. In order to multiply two matrices together using matrix multiplication, this condition must be met. So let's look at this bottom example here. It says the number of columns on the first matrix, so let's see how many columns. We have 1, 2, 3 columns, must equal the number of rows on the second matrix. We have 1, 2, 3 rows. Since the number of columns here equal the number of rows here, we can perform matrix multiplication. This was crucial and the reason why we're not able to multiply A and B together in this example. So remember, A and B are both 3 by 2 matrices. If I wanted to do A times B, it says there are incorrect dimensions for matrix multiplication. So as you can see here, the number of columns in A, there are 2 columns, but there are 3 rows in B. The number of columns of A do not equal the number of rows of B, meaning we cannot perform matrix multiplication. So let me explain what matrix multiplication is. Essentially what we do is we perform what's known as the dot product for various combinations of corresponding rows and columns. So that might sound a little bit confusing for people not familiar with this type of mathematics, but let's see exactly what I mean. So let's take a look at this top left element here. When you multiply the matrices, this says we should get an 11. So how do we get that 11? So to get the top left corner element, aka the element in the first row and first column, we take a look at the first row of the first matrix and the first column of the second matrix. And what we do is we multiply corresponding elements together and add those results together in the end. So what you would do here, let's see, first you would do 2 times 1. So you would multiply the first element 2 by the first element 1. You would multiply the second element 3. Oh, geez. I don't know how that happened. You'd multiply the second element 3 by the second element 2. And you'd multiply the third element 1 by the third element 3. When you multiply all those together, and that's exactly what we see here, when you multiply all those together and add them together, you get 11. So that's how you'd get that element. And we can do the same thing. Let's try again for the bottom left element. Let's try the 17. So the 17 is in the second row and first column. So we look at the second row of the first matrix and the first column of the second matrix. And you multiply the corresponding elements. We get 1 times 1, which is what we see here, plus 2 times 2, which is what we see here, plus the 4 times 3, which is what we see here. And adding those results together will give us 17. And you would do the same thing for the top right corner and the bottom right corner. You would do that, and I have it shown here, to get this matrix here, which is the result of the matrix multiplication, which is exactly what we see. I'm going to exit out of this. Right, we just took a look on how you multiply matrices together using by hand matrix multiplication, but now we're going to take a look on how you multiply them together on MATLAB. So if two matrices C and D have the correct dimensions for matrix multiplication, the two matrices can be multiplied together using C asterisk D. Notice there's no period in this case because this is actual matrix multiplication. We're not multiplying corresponding elements. So if we look on MATLAB, I have C and D already saved. And these are actually the matrices from the previous example we used. So if I do C asterisk D, it will give me the 2 by 2 matrix result that we saw in the previous example, because this is matrix multiplication. This is not the array operation. We're not multiplying corresponding elements. Likewise, a square matrix can be taken to a scalar power by using the exponential. So if we have a square matrix Q, it can be taken to the kth power by using Q caret K. No period again. Notice that I said it must be a square matrix. This is because essentially what a square matrix does is it multiplies the matrix by itself and performs matrix multiplication. The only matrices that can be multiplied by itself, matrix multiplication, are square matrices, because the number of rows have to equal the number of columns if we want the dimensions to meet. So let's take an example. If we take our answer we have here and take it to the second power, so this operation will not square each element. It will multiply this 2 by 2 matrix by itself using matrix multiplication. And this is the result you get. And if you perform the math and you look at everything and you actually do the matrix multiplication, this would be the result you end up getting. Please note that you have to be conscientious of the difference between the array operations we discussed and the operations such as matrix multiplication or matrix exponentiation. The array multiplication and division is accomplished with a period. You have to use the period asterisk if you want to multiply corresponding elements. The matrix operations such as matrix multiplication or exponentiation do not have a period. Please know exactly what operations you're using, or else you're likely to get a lot of errors in code that you write in the future. All right, now we're going to shift gears a little bit and take a look at logical vectors and logical matrices. So a logical vector or matrix is a vector matrix that consists of only logical ones and logical zeros. A logical vector can be created by a variety of ways. So we can use the logical function as this example. We can say logical, and then in the parentheses, put this little vector here, 1, 0, 1, for example. We can actually try that here on the command window. So I can say logical 1, 0, 1, and that will give me a logical vector with exactly the elements we specified. I can also use the true or false function and I'll just kind of demonstrate it here. So the true function, if I do true and then put a 2, it'll give me a 2 by 2 matrix of logical ones, or the true number, for example. If I say false of 2, that would give me a 2 by 2 matrix of logical zeros. It's fairly straightforward using the true and false and logical function. Logical vectors can also be created by using relational operators. If you remember one of my previous videos, I discussed relational operators. Greater than, less than, equal to, all those operators, and we can get logical vectors by using those operators either with scalars or other vectors of the same length to produce a logical vector. Each element in the vector that satisfies the condition that you create will result in a logical 1 being placed in the corresponding element in the resulting logical vector. Each element that does not satisfy the condition will instead result in a logical 0 in the corresponding element. The best way to show exactly what this means is to just give an example. So here I have an example here. I have the vector 4, 2, 3, 9, and I perform the operator greater than 3. So what we do is we take a look at each element. The elements that satisfy the condition will give us a logical 1. So let's take a look at each element. The first element, 4, is in fact greater than 3. So the first element of our resulting logical vector will be a 1. 2 is not greater than 3, so the second element will be a logical 0. The third element, 3 is not greater than 3, so once again we get a logical 0. For the last element, 9 is greater than 3, we get a logical 1. And we can do exactly this on the command window to show that this is what we get. 4, 2, 3, 9, so let's type that out. So let's see, we got 4, 2, 3, 9 is greater than 3. We get the exact logical vector we would have expected. All right, let's take a look at this example here. So now we have the equals operator. So we can see the first 3 elements will clearly be 1s because 7 and 7 and 7 all in fact equal 7. 3 and 8 do not equal 7, so we'd get 2 zeros. 7 does equal 7, so we'd get a 1. So this would be the vector we would expect if we were to put this in the command window. Let's do that. 7, 7, 7, 3, 8, 7 equals 7. We get that logical vector. All right. Here we have just one more example. I won't put this one in the command window, but we can work it out. So 0 is less than or equal to 12. It is less than or equal to 12, so we get a logical 1. Negative 3 is less than or equal to 12, so we get a logical 1. 56 is not less than or equal to 12, so that will give us a 0. 12 is equal to 12, which is included in less than or equal, so we get a logical 1. 9 is less than or equal to 12, so once again, we get a logical 1. And if we were to put this in the command window, this is exactly what we would expect to happen. Now we'll talk about logical operators with vectors. So we looked at the relational operators and how to get a logical vector. But likewise, as I discussed in that same other previous lecture, we can use the logical operators, the and, the or, the not operators on various logical vectors. As opposed to single logical values, the logical vectors must utilize a different notation to complete the and or operators. To complete the and operator, instead of using the double ampersand that we used for just scalars, we're going to look at a single ampersand for vectors. And it will perform the and operator element-wise. So it'll look at corresponding elements of a vector matrix, and it will perform the and operator. A single vertical bar will be used for the or operator, and compute the or operator element by element. The not operator works the same as it would for scalar values. Essentially, it takes your logical vector and it flips the values of the ones and zeros. And we're going to do a couple examples just to kind of work this out. So let's take a look at this first example here. So we say the first vector 0, 1, 1 or 0, 0, 1. Remember, the or operator will result in a logical true if either or element is a logical 1. But you have to look at it element by element. So let's look at the first element of both vectors. The first element is 0, the first element is 0, so that means the first element in this produced vector will also be 0, since neither of them is a 1. Second element, first vector we have a 1, second vector we have a 0. 1 and 0. The or operator tells us that it will result in a logical 1. 1 or 1 for the third element results in a logical 1. So you see, you have to go element by element, and if you don't remember the or operator and what it does exactly, I recommend checking the previous lecture I had on relational operators and logical operators. All right, let's look at this now. Actually, let's perform this on MATLAB first before we move on. So I believe it was 0, 1, 1 or 0, 0, 1. As you can see, it gives us exactly what we expected, 0, 1, 1 for a logical vector. And we had to use a single bar. If we tried using a double bar, let's see what happens. Using the double bar actually gives us an error. It says that they have to be logical values, because those are for scalar values. All right, let's look at this next example. Now we use the and operator. So let's look at the first element, 1 and 1. They're both logical 1s, meaning that the and operator will give us a logical 1. Second element, 1 and 1. Gives us a logical 1 again. Third element, 1 and 0. Since this element is a 0, the and operator tells us the resulting vector is 0. 0 and 0. That will also result in 0. This is what MATLAB would give us. Let's look at this example. So first we have to perform the relational operator, then we perform the not operator. So essentially, let's see what would happen first. So if we did this vector is less than or equal to 3, we would get the vector, so 3, the only elements that work are the two 3s. So we would get 1, 0, 0, 1. And then when we take the not operator of that, we'll see that that will result in all the elements being reversed. So instead of 1, 0, 0, 1, we get 0, 1, 1, 0. And that's what MATLAB would give us. Then let's look at this final example here. So if we do 0, 0, 0, 0, 0, 0, 1, and 1, 1, 1, so if we notice, the dimensions don't match up. We have a 4-element vector and a 3-element vector. If we perform this in MATLAB, let's see what happens. So if we say 0, 0, 0, 1, and 1, 1, 1, it says that the dimensions must agree. So we cannot actually use the logical operators if the dimensions do not agree. It's just not possible, and it won't happen. Let's look at some logical functions for vectors. So there are certain functions that can take a logical vector as input and perform some operation. And I'm going to talk about 3 of them, and we'll do some examples. So the all function returns a logical true if all the elements of the vector or matrix are logical 1s, and a logical false if any element is a logical 0. So it's kind of intuitive. So basically, if you put a logical vector or matrix in the all function, it will only return a true if every single element is true, is a logical 1. If any one of the elements is 0, it will return a logical false. The any function returns a logical true if any one element of the logical vector is a 1, and returns a logical false if that condition is not met, meaning that every single element is 0. So if every element is 0, the any function returns false. If any one of those elements is true, it returns a true. That's kind of what any means. Basically means if any of the elements are logical trues, return true. Finally, we have the find function. This is probably the most confusing one to understand. But the find function returns all the indices of the locations of logical 1s in the input logical vector. This function is commonly used to find the locations of certain number in a vector. So essentially, it looks at where all the logical 1s are, and then it will give you actually multiple numbers for your output. It will give you a matrix of numbers for your output. And we're going to do an example to show exactly what this means. But let's say if we had a logical, let's do a very simple example real quick in MATLAB. So if I were to say find, and then I gave 1, 0, 0, 1, what it'll do is it will return me the indices of where the logical 1s are. As you can see here, we have logical 1s in the first element and in the fourth element. So the output will be the numbers 1 and 4, which is exactly what we see. There's a logical 1 in the first position and in the fourth position. Let's try another example. Let's use the all function. If I use all of 1, 1, 1, 1, it gives me a logical 1 because all the elements were true. But if I do all of 1, 0, 1, 1, 1, 1, oops, 1, 1, 1, it gives me a 0 because one of the elements was 0. Not all of the elements were true. Finally, one example with any. If I did any of 1, 0, 0, 0, 0, since just one of the elements were a logical 1, meaning any of them were 1, it returns a logical true. And then I have a few examples we can look at. So all of 5, 4, 8 is greater than 3. So what would this be the same as here? So we can see that instead that would be the same as all of, what do we get? So 5, 4, and 8 are all greater than 3, meaning that would result in 1, 1, 1. That's the vector we would get. Since all of them are 1, the all function will result in true because all of the elements in this logical vector are true. Let's look at this next example here. So we say any 5, 3, 1, 3 equals 3. This would result in any, and then what would this result in? So 5 does not equal 3, 3 equals 3, 1 does not equal 3, and 3 equals 3. The any function tells us that if any of these are logical 1, it will result in true. That means that the answer is going to be true because 2 of them are true. Let's look at this example. Any not 8539 is greater than 2. So this one has quite a bit we have to deal with here, but let's take a look one step at a time. So any not, let's look at the first thing here. So we say 8539 is greater than 2. Well, all of those elements are greater than 2, so this will give us a logical vector with 4 1s because 8, 5, 3, and 9 are all greater than 2. But then what we have to do is we have to perform the next operation, which is the not operator. So that will do any, and the not operator will flip the value of every single number in there. So instead of 4 logical 1s, we're going to have 4 logical 0s instead. Then if we perform this operator, you'll see it'll be any of 4 zeros. Since none of them are logical true, the answer is going to be false, because any requires that at least one element must be true. Here we go. Let's see. Find 0, 1, 0, 0, 0. As we did on the example in MATLAB, this will actually produce one number, and that number is going to be the location of the logical 1. The 1 is located in the second element, meaning that this will give us not a logical, it'll give us the number 2. Let's see what this will give us. So, if we did find, let's see, what will the operator inside give us? So it will give us, let's see, we're going to say it will give us a logical 1 for any value that equals 4. So we have 0, 0, since 3 or 9 does not equal 4, a 1, 0, 0, 0 for 1, 2, and 5, and then 1, 1 for the 2 4s at the end. So this will give us the 2 values, the 3 values where there are logical 1s. So let's see, where are the logical 1s? There's a logical 1 in the 3rd position, so it'll give us a 3. So the 3rd, 4, 5, 6, 7, 8. So there are also logical 1s in the 7th position and the 8th position. So that's what's going to be result of performing this. And let's see if we can actually perform this on MATLAB. If I copy, go over to MATLAB, if I were to paste it, 3, 7, and 8. It's exactly what we would expect. Now I'm just gonna talk about some of the other functions that can be used for vectors and matrices. So some functions operate differently depending on whether they're given a vector or matrix. And these are a few examples of functions that do so. So let's take a look at some of them. First, we're going to start with the sum function. What the sum function does is it essentially takes a look at your vector and returns the sum of all of the elements being added together. So if we were to go to MATLAB, I have an example vector we can use here. If we were to take the sum of this, it'd be 5 plus 1 is 6, plus 3 is 9, plus 7 is 16. We should get 20 as our sum. If I take sum of vec, I get the sum of all of the elements, 20, which is exactly what it does for a vector. But when given a matrix, it returns the vector of sums of each individual column. So it'll give us a new vector that is the sum of each individual column. So let's take a look at the matrix we started with, mat. So this will return a vector that has the sums of each column. So in the first column, we'd have 9, then 8, then 7. So if I do sum of mat, I get 9, 8, 7. The length function. When given a vector, it returns the number of elements in the vector. So this one's very useful if you want to know exactly how many elements are in your vector. So let's take vec. If I were to take length of vec, I would get 5 because there are 5 elements in my vector. But let's say I took mat. What mat will do is it will look at your rows and your columns, and whichever number is bigger, it will give you that value. So we have 2 rows and 3 columns, meaning that length of mat will return 3, because 3 by 2, I mean, this is a 2 by 3 matrix. 3 is the higher number, it will return 3. The max and min function, when given a vector, returns the max / min value in the vector. So if we had a vector, for example, let's look at vec. The maximum value in here is 7. So if I were to say max of vec, I get that max value, I get 7. If I were to look at a matrix again, so let's look at that matrix, so mat, it will give me the max value in each column. So if I were to do max of mat, in this column, the max element is 7. In this column, the max element is 5. And in this column, it is 4. So that gives us that vector. Likewise, there's a very similar min function, which does the same thing. So if I were to type vec and then min of vec, I would get 1. And you could do the same thing for matrices. It's just the opposite. It gives you the minimum value. All right. And now, since my internet's annoying, we're going to disconnect and try again. There we go. Some more other functions. So some are only useful when you're given a matrix as an argument. Here are a few examples. So we have the cum-sum function, which returns another matrix of same dimensions that contain the cumulative sum when adding the elements of each column singularly. So once again, the only way you can really see this is by giving an example. So let's look at this, well, let's actually clear. Let's look at the matrix B, for example. What the cumulative sum will do, let's actually show the result. So if I take the cum-sum B, What it does is it adds all the elements in the column one step at a time and returns all the check marks along the way. So look at here. So we start with 7 and 4 again. But 7 plus 12 is 19. So it puts a 19 in the second element. Then it adds that 19 to 8, and you get 27. So 7, 19, and 27. In this column, you have the 4. 4 plus 6 is 10, so you get 10. Then you add the 8, and you get 18. So it returns the sums each step along the way. And you can do something very similar to comprod, commin, commax. All of those will do the exact same thing. So if I do, for example, comprod of b, it will return the results where I multiply one step at a time. Or for example, if I use let's look at the matrix. Oh, not that one. Let's look at b. If I were to do the cumulative max function of b, it gives you the maximum at each step of the way. So if you look at the first row, the maxes are 7 and 4. By the second row, 7 is no longer the max of the first column, it's 12. But 6 is the max of the second column, so it's 6. By the next step, in this column, 12 is still the max, so it returns 12, but in this column, 8 is now the max, so it returns 8. And it does the same thing for the minimum using the cumulative minimum function. The size function returns 2 arguments. Oh, geez. Returns 2 arguments, the number of rows and the number of columns in a given matrix. So it takes a look at your matrix and gives you the row number and the column number. So if we look at mat, this is a 3-row, 2-column matrix, 3 by 2. So size of mat will give me 2 rows, 3 columns, a 2 by 3 matrix. So here we also have the flip LR function. And what that will do is it will reflect a matrix across the y-axis, essentially meaning it will take your matrix and it will flip it left and right. So let's take a look at mat again. So if we use the flip LR function, it will actually reverse the order of the columns. So flip LR of mat. So you can see the last column becomes the first column and the first column becomes the last column. The rows are not affected. You're simply just flipping the column order in that case. We can do the same thing with flip UD, which instead reflects the matrix up and down across the x-axis. So let's take a look at mat. If I were to use flip UD here, flip UD of mat, it will instead reverse the order of the rows. The bottom row becomes the top row becomes the bottom row. The columns are not really affected in this case, it's just flipping it up and down like so. Then finally, the rotate 90 function rotates a matrix counterclockwise 90 degrees. So let's look at an example. So if I did rot 90 of mat again, it will essentially rotate it counterclockwise. So that means that the last column becomes the top row and the first column becomes the bottom row. It's just rotating it. Let's see, the reshape function returns the given matrix reshaped into different dimensions. So for example, if I said reshape mat 3, 4, it will reshape mat, this matrix, into a 3 by 4 matrix. However, the number of elements must allow for the reshape to work properly. So let's say, for example, I have mat. There are 6 elements, so I could say reshape mat into a 6 by 1 matrix, 6 rows and 1 column, and it will reshape it like this. The reason it worked is because 2 by 3 and 6 by 1 have 6 elements each. But if I were to do, say, reshape mat 3 by 4 in this case, I don't have 12 elements. So it'll say to use the reshape number, the number of elements must not change. So I cannot use that function. A couple other final functions. The rep mat function replicates a given matrix into given dimensions. So it will take your matrix, your whole matrix, and copy it over to produce a larger matrix. So if I said rep mat 3, 4, it would create a large matrix that could be thought of as a 3 by 4 matrix of the matrix mat. So let's see exactly what I mean. So let's take a look at mat here. If I were to say rep mat, take my matrix mat, and then say 3 by 4, now there's a lot to look at here, but essentially it copied this smaller matrix into a giant 3 by 4 matrix. So if you look at these elements here, 7, 5, 3, 2, 3, 4, that's my starting matrix. and it's copied over into 3 giant rows and 4 giant columns. I can also use the replm function. It replicates each single element from the matrix with the specific dimensions. So replm mat 3, 4 would create a large matrix that could be thought of as multiple 3x4 matrices of each element in the matrix mat. Once again, that's hard to kind of verbally understand, but if I take, oops, not ma, I want to do mat. If I do mat and then say replm mat 3x4, it creates a 3x4 matrix of each single element. So 7, it creates a 3x4 matrix of 7s, a 3x4 matrix of 2s, a 3x4 matrix of 5s, etc., etc. So it replicates the single elements, while the repmat function replicates the entire matrix. And those functions are all I have for you today. Thank you so much for watching.